Hello. You can unmute yours from here.
Oh, I will do it.
Yeah, it's okay.
So we have been consistently running 10-15 minutes delayed. So. Okay, so are you used to it? Oh yeah, so okay, just like so this won't be the first session.
The less people, the better for me. The less people, fewer people, better for me.
The less people? No.
Oh, no. Full audience. Hello, everybody. Welcome to the next session. My name is Christina Pepper. I'm a faculty here at NYUAD, and it's my pleasure to chair the next session on network security. We will have 3 talks. The first one will be on network address translation detection, which will be given by Tomasz. We will have 2 further talks about anomaly detection in networks and on a dark case study. So this sounds very interesting and I'm looking forward to the talks. So welcome, Tomasz, thank you.
Is it working? Okay. So, hello, my name is Tomáš Komárek. I'm from the Department of Computer Science on Czech Technical University. And in this presentation, I'm entitled Passive NAT Detection using HTTP access logs. I'm going to show you how to construct a reliable NAT detection system. Here's the outline of the presentation. Firstly, I will briefly explain what NAT is and why network administrators should be informed about NAT devices in their computer networks. Then I will describe the proposed NAT detection system, and finally I will present you how it works on real network data. Okay, so what NAT is? NAT is an acronym for network address translation, and in simple terms, this technique enables hiding more network hosts behind a single one. In this picture, there we have an example of a network which includes a NAT device. It's a host C, highlighted with the red color. And from network administrator point of view, who is sitting on the perimeter of the computer network, in this case on the proxy server, there are only 3 hosts, host A, host B, and host C. All of them appear like end hosts at first sight, and also all of them are uniquely identified in the data by its IP address. However, in reality, host C is a NAT device which hides more NATed hosts behind. And these NATed hosts are not recognizable at first sight, since all of them share the same IP address. There are several reasons why NAT devices are used in computer networks. For example, they help to overcome the problem with the deficit of IP addresses. They provide content filtering. They hide inner network topology, and so on. Nevertheless, the unauthorized NAT devices, especially with insecure configurations, are considered as possible vulnerability, as they can allow unrestricted access to the network, and moreover, the potential malicious activity of intruders would be hardly recognizable, since it would be mixed up with the activity of other NATed hosts. Another reason to detect NAT devices is that they confuse advanced systems based on behavior analysis. One example of such system is a NAT, is an anomaly detector. Anomaly detector model behavior of normal user or normal behavior of network hosts, and then report deviations from that behavior. In these systems, NAT devices cause false alarms, as their behavior is not the behavior of one network host, as it is expected, but it is the behavior of multiple ones. Therefore, they cause false alarms. So these two particularities motivate us to detect NAT devices, and it is a simple binary classification problem, since each host in a network is either end host or NAT device. NAT device is, in our case, the positive sample, as it is a class of interest. A lot of prior work has been done in this area. The approaches can be divided into 2 groups, signature-oriented and behavior-oriented. The signature-oriented are usually based on some observation or expert knowledge. For example, it is known that initial TTL values of packet header fields are specific to some operating systems. So when we see 2 different TTL values coming from one IP address, we may suspect that behind this IP address there are more or 2 different operating systems, and thus it's possible that this IP address is not device, as there is more users which use different operating systems. On the other hand, the behavior-oriented method, where also our proposal belongs to, are exclusively based on supervised learning. These methods collect statistics about host behavior within a specific time window, and after that time window, there is a learned decision rule deciding to which class the behavior corresponds. The disadvantage of signature-oriented method is that they usually struggle with detecting NAT devices where all NATed hosts share the same operating system or same browser and similar things. And the drawback of behavior-oriented methods is that they require labeled data, which can be hardly obtained in network security domain. Our contribution to this area is twofold. Firstly, we developed a more robust representation of host behavior, which reduce the number of false positives. And we also use a method that turns unlabeled data into labeled ones. So this means that our method requires only unlabeled data, which can be easily obtained. Okay, so as a source of our data, we use HTTP access logs. These logs are produced by web proxy servers that capture communication between a network host and web servers. Therefore, one log entry corresponds to a request made by a host to a web server. There are fields like host IP address, server IP address, URL, user agent string, unlabeled, uploaded, downloaded bytes, duration of the communication, ending time of communication, MIME type, HTTP method, status, and so on. All the fields are extracted from HTTP headers. So from privacy point of view, it is important to know that these data are considered as telemetry, or also called metadata, as they do not include any information regarding content of the request. So in other words, we do not need to do deep packet inspection in order to resolve whether the user or the host is end host or not device. On this slide, there is a scheme of the proposed detection system. It's quite straightforward. At the input, the detector is fed by HTTP logs. The first part of the detector extracts the feature from these logs. The features are collected in consecutive non-overlapping windows. The windows cover the time period of 24 hours. And after that period, we select only one representative window based on quantile. I will describe it in more detail on the next two slides. Using this representation, the next classification part assign labels to each individual IP address identified in HTTP logs. So now I'm going to explain the host behavior analysis part. So from each log entry and for each host, we extract a collection of 8 features within a 30-minute time window, and we count the number of unique contacted IP addresses, the number of unique user agent strings, the number of unique operating system, including their versions, the number of unique internet browsers, persistent connections, the number of uploaded and downloaded bytes, and the number of sent HTTP requests. Now, unlike the previous work, we do not make the decision based on this one window, but we collect more windows which cover 24 hours. So there will be a sequence of windows. Specifically, there will be 48 windows for each feature. And from this sequence, we select one representative windows according to 90% quantile. The reason behind that is that we want to avoid misleading extreme values, which cause false positives, because the extreme value would correspond to 100% quantile. So this means it will be the highest bar. But this bar, or this one window, can be caused by abnormal short time user behavior. For example, user can change with respect to these features. For example, the user can change its operating system. It can upgrade its internet browser or download a huge file. So therefore, we select only 90% quantile. And we do this for each feature. So at the end of this process, each host or all hosts in the data will be represented by feature vectors with 8 components. And to classify the host in the network, we use a linear classification model called support vector machine. We decided to use this classification model as it is largely insensitive to mislabeled training samples. I will comment it later. And in order to learn this decision rule stated in the first equation, we have to solve the optimization problem in the second equation. But this problem, this equation requires labeled data. It's the xi and yi. And the data itself is very easy to collect, is very easy to obtain because we can just collect the data on proxy server. But the difficult part is to annotate individual data. So there is a problem with labeling because manual annotation is feasible only for huge NAT devices, as there is enough evidence in the traffic. So the network administrator can see that this host uses a lot of operating systems. There is a lot of internet browsers. So it's clearly that this host is probably not device. But it's not easy to say or make a verdict whether a small device, especially when the NATed hosts have the same operating system and the same internet browser, is a NAT device in fact. And even if the network administrators have a knowledge of inner topology, there still can be unauthorized NAT devices. And even if somehow we gain the labeled data, there is another problem with training because the data are usually highly imbalanced. This means that there is far less NAT devices compared to the number of end hosts, which makes a problem for training. In the best scenario, we would like to have rich samples from both classes of behavior. By rich samples, I mean NAT devices of different sizes. So, for example, we would like to have one or several NAT devices of size 3. So it means that there will be 3 NATed hosts. Then of size 5, that there will be 5 NATed hosts, and so on. But this is not the typical case in real networks. So to overcome this problem, we decided to create artificial samples, artificial positive NAT devices. And we do it in these 2 steps. Firstly, we mark all hosts in the data with the negative label, and then we merge logs of negative samples in order to create artificial NAT. The only assumption is that the vast majority of hosts in the data should be end hosts, which is a valid assumption for regular networks. So, and in such way prepared NAT detector, we evaluate it on real network data. We have two types of data at our disposal: the unlabeled traffic captures and labeled traffic captures. The unlabeled data are collected from 4 networks, which are of different sizes. we have a network with about 3,000, 5, 10, and 25,000 of hosts. And the data were collected from 2 days, which were spaced by 1 week. We mark all the hosts in the data with the negative label. And in addition to them, we generated positive samples by merging their logs. And we do it in such a way that we generated a balanced data set. So this means that in the case when there were 3,000 of hosts, and we mark them with negative labels, so we mark them as they are end hosts, we generated another 3,000 of NUT devices. And we were generating in such a way that we were merging logs of 3 up to 12 hosts. And we uniformly distributed the NUT sizes. And we also use sampling with random sampling with replacement. Once we learned the detector on this training data, we also test it on this data, but from the second day. But what is more important, that we also test it on the labeled traffic captures from real network. We did it because we wanted to see whether the detector learned on artificially generated samples can be used to detect real NUT devices. And here are the results from 5 experiments. The first experiment is called time drift, because we were just simply training the detector on the first day, on the samples from the first day, and tested it on the samples from the second day. This scenario was also conducted by our prior art. But we consider the second scenario to be more important. We call it cross-validation, because we were learning the detector on samples from 3 networks, and then we were testing on the fourth one. And we do it for all combinations, and we showed the worst case. This scenario simulates the situation when we learn the detector on our network and we want to use it on previously unseen network. So we considered this result as the representative one. We also test the detector on hosts with having the same operating system, especially when the NUTted hosts have the same operating system, and also having the same operating system and internet browser, which is the difficult case. As you can see, the measures are a bit worse, but still good. And in the final experiment, we tested on real network data, or on data with real NUT devices. And as you can see, the results are even better than in the case of artificially generated. Here are some additional results. The top bar graph indicates that it's pretty hard to detect NUT devices of small sizes. For example, we weren't able to detect NUT devices of size 3 in 37% of cases, but there is a nice exponential decay. So for example, NUT devices of size 6 were detected almost in all cases. The second graph is more interesting one, because it shows how much or how many real NAT devices can be present in your data, in your training data, which you are going to mark as negative samples, as you don't know which are the ones. And as you can see, you can mislabel about 20% of data, and the accuracy will be still good. Okay, so the conclusion is that unlabeled HTTP access logs of large network containing 20% or less of real NAT devices can be used for construction of reliable NAT detection system. And for those who are not interested in network security, the conclusion might be that sometimes it's a good idea to generate samples in artificial way, and also that it can be helpful to collect more evidence in order to make a decision about the behavior. So that's all for me, and thank you for your attention.
Thank you. We have time for one or two questions.
In your case, you're using 24 hours of samples to make a classification. And have you tried to see what's going to happen if the window is going to get smaller? I mean, how many hours do you need for reliable classification? Have you tried to take a look at this?
Yeah, we tried, but we decided for 24 hours as it is aligned with the human behavior. Because if we were deciding, for example, after first 6 hours or 10 hours, the host might be sleeping. So we were classifying NAT devices as end host because there were no activity.
This can actually change. I mean, within 24 hours, you can have one device after NAT, or maybe 2 devices or 3 devices. So this can change over time. So this is not necessarily not necessarily stable over time. But I was just curious, how much shorter can you make the window to maintain good accuracy?
Okay, I understand.
I mean,
we were experimenting at the beginning, similarly as the previous work. We were using just one time window, so it means we were doing a decision after 30 minutes. Mm-hmm. But we observed that it's better to collect the data for the whole day and then we make a decision.
Okay, and could you tell us, for instance, what was the accuracy when operating on 30-minute windows?
It was slightly worse. The difference wasn't huge, but it depends on the data. But it was slightly worse, like 5%.
5%, okay. Thank you.
You can also take that offline to discuss that afterwards. I have a very short question that I would like to add. You showed that there were like 8 different features that you took into account for the classification itself. Exactly. Are there? Did you reevaluate these features regarding if there are some of them that a device
that are more important? Or?
So are there some that can be spoofed more easily or can be falsified by a device that pretends to be a normal host, but is actually a NAT, so it tries to disguise of being a NAT? So are there ones that are more secure in that perspective or less secure? Did you evaluate that in any way?
No, we haven't. The only one what we did is we were evaluating it on NAT devices where all NATed hosts have the same operating system and internet browser. Mm-hmm. So this means that we were removing, or there were only one feature. The user agent was still the same, because from the user agent we parse the operating systems and internet browsers. Okay. So these 3 features were like removed.
I see. Okay. Thank you very much again. And then we come to the second talk of the session. So the second talk of this session will be given by Gabriel Macia Fernandez, who will speak about statistical network monitoring for anomaly detection.
Okay, thank you. The work that is done in the University of Granada in Spain, I will try to point only to that screen in order to get. Thank you for your effort after having lunch. I will go directly to the motivation of the problem. This problem is, the problem we're trying to solve is in the context of network monitoring. This is an example of network, and this networks could be very complicated, but this is a very simple example in which we can observe several routers belonging probably to different corporate networks. In this network, if we want to monitor all the events that happen in this network, we will have a different set of different events. For example, routers are generating net flow logs regarding the different flows, TCP, UDP flows, and they are sent to specific systems designed to collect these logs, which are called CMs. Moreover, we can collect logs from intrusion detection systems or firewall logs that protect corporate networks. But normally, these systems, CM systems, are designed to collect these three types of information, but there is a lot of multiple additional information that could be collected. For example, all the syslog information in a PC, or antivirus information, personal firewalls, even logs from Windows, or even hardware monitor that shows the CPU load, memory usage, and things like that. In these systems, there are mainly three problems in the current technology. The first one is the scalability problem. Imagine that we have only a single CM in all internet, in the whole internet, collecting all the information from the different PCs, routers, and equipments. It would be almost impossible to correlate all the information coming from so huge number of devices. Even more, if every device includes a lot of features, as it is growing, it is a more complicated task. The second problem is a problem of the transferring of information. If we want to send all this huge information periodically and frequently to the CM, it is wasting a lot of bandwidth information in the network. So we will to reduce this kind of information. And the third problem is a privacy problem. Imagine that we have only a single CM in the whole network. Perhaps all the companies are sending this information to the CM in order to correlate all the information about attacks. In this scenario, companies will be probably reluctant to send all the information to another third party. So there is a privacy concern here. Even more if we plan to leverage the CM as a service as a reality in the internet. So our work deals with these three problems. And first of all, we recently published in the Computers and Security Journal, we published a methodology called Multivariate Statistical Network Monitoring. This methodology is really an adaptation from a well-known methodology in the industrial area for process control. The methodology in the industrial area is called Multivariate Statistical Process Control, and our name is taken from that. It is really, I will be detailed in the next slides, but the pioneer work by Lakina did an adaptation of the principal components analysis methods to network analysis. And we took this idea to develop this methodology. So what is this? What is MSNM? Really, there are several steps in the methodology to analyze the network information. The first steps are data preparation and PCA decomposition. This is really to collect the data and prepare for the analysis. I will give details in brief. After having the information decomposed by principal component analysis, we obtain 2 statistics for every observation, only 2 statistics. And this is very important because this is a very high reduction in the amount of information we are going to send in the network. Then with these 2 statistics, we will be monitoring anomalies and detecting and saying, okay, here we have an anomaly. Normally, data mining and big data approaches to this problem stop here at monitoring and saying, okay, I have a problem at this point. But this methodology allows us to go further and make the diagnosis of the problem. That is, when we point that we have an anomaly, we are going to extract which are the features and which are the causes, the root causes for this anomaly. So from a forensic point of view, this is really important because it is not only a matter of processing a huge amount of network traces and pointing here is the problem, but also saying here is the problem because you have a big amount of, for example, email or a big amount of scanning attempts. So let's go step by step just to understand briefly which are all the steps. The first one is the data preparation. Our target is to build an X matrix where the rows are made of observations and the columns are features. What are observations for us? Here the observations are the items or entities that may be identified as anomalous or normal. Our interest is translated to observations. For example, we could have here a row for every minute of network traffic. So time interval would allow us to detect anomalous intervals of traffic. But here we could select, for example, IP addresses, source IP address, for example, to identify insider threats, or destination IP to identify attackers exfiltrating information from a network. Ports, of course, to identify non-legitimate services, or so on and so forth. The other issue is are the features. The features are parameters that we extract from the network information, and we opt for the feature as a counter strategy. That is, all the features collect the number of times that a certain feature appears in a given event or window. So here we could have features like the group of a number of times that a group of IPs appear in a given minute, or the number of ports per application, number of accesses to the 80 port HTTP, or things like that. So this is the first step in the methodology, building this matrix. The next one is decomposing this matrix X. This is this in the figure, decomposing using principal component analysis. Here, we decompose the normal strategy with the principal component analysis is to decompose the matrix in a matrix of scores called T, multiplied by a matrix of loadings called here P. So this is the score matrix is really the compressed representation of X in another subspace, and this allows to reduce the information. In many research approaches, PCA is used just to reduce the information, the huge information here, to a more compressed version. But we are not interested only in this reduced information, but also in what we call the residuals. That is the rest of the part that we are losing by modeling for this part of the matrix. So we will monitor, we will take now one statistic collecting the information taken from the model, which are represented by the scores, and other statistics for the residuals. So how is it done? What we really do is to take for every observation, every new observation coming into the monitoring system, we take one statistic considering the different components here of the score matrix and the different components of the residuals. And we apply, this is the vector of scores and this is the vector of residual. Then we calculate this to statistics, D and Q statistic. And this is really the quadratic sum normalized here and non-normalized for the residuals of the different components of the vectors. So just with these two statistics, we build what is called the Shuar Graphs, in which we represent for the D statistic and for the Q statistic, we represent the evolution in time of the statistics according to the different observations that we are getting into the system. So here we choose different levels of significance levels. This is for the 1% and this is for the 5% level of significance. And all the samples which are above these levels are really an anomaly. So here I can say that this is an anomaly, this one, everything. So what happens when we signal that this is an anomaly? In this minute, for example, consider that these are the observations and we have minutes. In this minute of traffic, you have an anomaly here. So what happened here? You go then to the diagnose step. And in this step, you use the contribution plot, which is you assign a score to every feature. Here we have represented the features, the different features in this problem, and we are setting that the feature number 15 and 24 are the responsible features for having such an anomaly. So finally, with this methodology, we are allowing to process a big amount of information. So the whole system in which we use this approach, this methodology, is like this. We have here the same network as before in our example. And then in this network, we have this sensor, this processing for MSNM. So where the steps are every minute, for example, every observation, all the components in the network send information to the processor, and the processor is able to compute the anomaly score based on the two statistics and diagnose every possible anomaly. So this is the standard approach for the detection. Obviously, in this approach, we have two problems. The first one is the network load problem, because we still have to send all the logs to the CM. And the second still remain the privacy concerns here. So what is our solution to this problem? Our solution is trying to use a hierarchical approach of this problem. So instead of having only one processor here, we are going to locate processors in every of the devices we have in the network. So first, if we compute both statistics D and Q here, we make a model of the behavior here for this device, and everyone is generating their own statistics. Then the next step is sending the statistics to an upper level in the hierarchy. This upper level is equipped with a new processor, and this processor is taking into account the model of their own logs or information, plus the information coming from the different subset of devices here. So it is adding to their own features, it is adding the different D and Q statistics coming from the devices. So finally, it compiles a new D and Q, and it sends the D and Q statistic to the final CM processor. And this is done for all the network. So finally, have a look here, and you have a global network, but we are only receiving here 1, 2, 3, and 4 pair of statistics. Only 8 features. We have reduced considerably the problem. Obviously, this is good in the slide, but there are certain questions. Privacy is really guaranteed. Why? Because the system is receiving only 2 numbers from a complete network, only 2 numbers. But what can we say about the detection performance? Is the detection guaranteed still, or what happens with the load reduction? So in our paper, we have evaluated the load reduction first, and analytically it is easy to obtain that we are sending only 2 statistics per node in compare with the number of n features per node. So here we have a high bandwidth reduction. But in terms of the computational cost, we have obtained as well that whenever the number of features m is higher than the number of sensors in the network, we have a reduction even in the computational cost. So it is worth, and it is working. But the main question is, are we affecting the detection performance or not? So for solving this question, we have developed an experimental environment, and in this environment, we have developed a network. This is a virtual network composed with this topology. Here we have we are simulating a corporate network, complete corporate network with a border router, and 3 subnetworks, 1, 2, and 3. Everyone with 30 client machines, generating traffic to 100 web servers in the internet. There is an attacker who is going to strike attacks in the network. And we have a DM set placed with a web server. In this scenario, we have built a data set. This data set is 45 hours of normal traffic, synthetic normal traffic, 1 hour of attack traffic. The attack traffic contains denial of service attacks, both high and low rates, in order to see if we are able to identify both kind of rates. We use the HPN3 tool, and we also implement scans attacks, SYNC stealth, with Nmap tool, and data exfiltration attacks, several different kinds. So for data exfiltration, we implemented we used a common exploit for Windows in the Metasploit framework using the payload reverse TCP on port 4444, which is the standard. In summary, we got a data set with more than 6 million of connections in the NetFlow format. And we carried out the experiments here just to see the detection results. The data set is divided into 3 subsets. The first one is the calibration, just to build the model, the PCA model. This is of 22 hours. Then we tested the calibration, we tested the model against a test set of 1 hour and a half with no attacks, just to see if false positives appear here. And finally, we used a 1.5 hours anomaly subset, just to test the detection results. So the results are shown here. Let me have a pause here just to explain the meaning of the results. In the upper row, we have the standard detection, that is the system in which we send everything to a centralized point. And here down, we have the results from the hierarchical approach. This is the D statistic, and this is the Q statistic. So here in the standard detection, we can see that there are above the control limits, we have 4, 1, 2, 3, and there is no more anomalies here, but in the Q statistic, we can signal here a fourth anomaly. So we have four sets. These four sets are identified clearly here in the hierarchical approach detection. For example, here in the Q statistic, we can see that the first amount is corresponding to the denial of service at a high rate, and the second is the denial of service at a low rate. These are port scanning, and this is the exfiltration. So finally, we are detecting the same results here in the hierarchical approach than in the standard approach. So to conclude, this hierarchical approach exhibits several benefits. It is able to solve the problems pointed out in the first part. Why? Because there is a considerable load reduction in terms of bandwidth and processing load, and it also guarantees privacy. Finally, this is the most promising result. It maintains detection capabilities. However, we have promising results. We are not too optimistic because we are aware that these results are taken with synthetic traffic. So we are now generating as an ongoing work. We have developed the experiment and we have obtained a data set in a real Tier 3 ISP. So that we are now currently contrasting the results in a real traffic. And the results are really similar, although other problems are appearing. And thanks for your attention. If any question?
We have time for a question.
Thank you, Gabriel, for the presentation. My question is about what happened with web attacks where many bonds in the network are involved. So because you are doing kind of an aggregation, so you lose some information. So how it works in this case, the approach?
Yeah, you mean in the scenario of botnets, for example?
Yes,
or distributed denial of service. Yeah, the power of the PCA model is to use multivariate models that are correlating all the information that happen in different places in the network. I put you an example. It is not the same if I monitor only levels of traffic in a given subnetwork. It is better if I can monitor the level here and the level in other place. And then I correlate the information. If normally an increase in the information in this network is in parallel with the increase of information in other, an increasing in both could not be an anomaly. But if one is higher traffic and the other not, we have an anomaly. So the power of multivariate methods is precisely the correlation between all the variables.
I think there was a second question in the back. Yeah. Okay.
Thank you. So in many cases, the contents in the internet actually changes very rapidly. And it seems like in your example, the data set you use to build the model and the test and then the attack traffic are actually continuous time, right? So how long is the model build valid?
Yeah, the model, you could build the model in a static way. That is, you take a set of hours, for example, 24 hours, and you build the model, and you apply the model for all the time. But you can also update the model dynamically by considering you give a weight to the model in the past 44 hours, and you are going updating the model with the new traffic. So the methodology is considering that you get a new bunch of network traffic connections, and then you filter these connections in order not to include anomalies in the normality model. And then you update the model. So you dynamically are continuously varying the model. In our current experiments, we are considering a data set of 3 months, 3 complete months, because the models vary from day to night, and there is a variation there. So we are dealing with this kind of problems just to build really feasible models.
Let's thank the speaker again. Then we come to the third talk. We're slightly moving from an anomaly detection to a real darknet study, so to the malicious side.
This is for August. It's in the pocket. Okay. Thanks. This one works. Okay. Okay, that's fine. So, hello everyone. My name is Abdelkader Lamadi. I'm associate professor at the University of Lorraine in France. And I'm going to talk about a work which was done by Marc Caudriot from the NSPICE, myself and Jérôme François, my colleague at Teneria. So the work is about topological analysis and visualization of network monitoring data. In this work, we considered the case of use case of darknet. So I will explain what is a darknet. The overview of my work, the presentation will be in the beginning a motivation, some context, the background and the related work regarding this issue, the methodology that we applied, some experimental results, and finally I will conclude and give some points about the future work. Monitoring data as detailed explained by Gabriel in the previous presentation, basically is widely used for security, forensics, and anomaly detection. It consists in collecting a lot of information from the network, basically flows, net flows, packets, syslogs, and whatever. So all the data that is in relation and related to the network. And the major point is to identify malicious activities like traffic patterns, malicious traffic patterns, and then to trigger alerts. So like an EDS or an IPS, this is the basic schema for this kind of system that are processing this network monitoring data to trigger alerts. In this work, we are focusing in a typical, another type of monitoring data, which is the Internet Background Radiation, IBR. It is data collected by what we call network telescopes and darknets. This traffic is usually noisy, but important source for forensics. I mean, to extract information, useful information for the security. The volume is considerable and with a wide range of services and sources. And usually it is a little bit challenged and difficult to extract the structure and compounds of this traffic because it is noisy, it is mixed, so it mixes of a lot of services, of sources. And the second point is to use this kind of compounds and extracted information to predict and model the internet malicious activities. So it's an important source of information basically for people who are working on security of networks. So a darknet, what is? It is usually a set of IP address, which are not used for productive network. All the traffic sent to these unused IP addresses is not legitimate because there is no service behind. So it's just the IP address to collect traffic from the internet. So the sensor, which is associated to this darknet, is silently collected all incoming packets without replying to any of them. So we take this figure. So here we have some scanners, large-scale scanners. So it's a set of machines which are scanning the internet, looking for open communication ports to exploit them and identify the vulnerabilities with these ports to make exploits. We can also have a lot of machines abused by an attacker to make a DDoS against an IP address. So our darknet is able to observe this traffic because we have these IP addresses. So we are a target to these scanners, and also we could be a target to this kind of DDoS. So this is a sensor, it's a machine or more, one or more multiple machines which are collecting the traffic addressed to this set of IP addresses. And then we have some tools to visualize, to analyze this darknet traffic that we are collecting. So this is basically darknet. In our lab, we are hosting one. It's a /20 darknet. So we have approximately 400 IP addresses that are collecting traffic. And the problem what we addressing this work is what are these compounds of the darknet traffic, what we can observe and what we can extract, and how to filter this traffic, to extract the types of malicious activities. So this is the main problem regarding this collected darknet traffic. There is many work regarding the characterization of darknet traffic and IBR in general. Basically, there is work from Pangyo in 2004, where they studied the composition of observed protocols and ports in IBR traffic. More specifically, they did a probabilistic study to observe DDoS attacks with a telescope or with darknet. And there is another recent work in 2010 where they make also another characterization of IBR traffic over multiple darknets to extract some feature and the level of pollution of destination IP addresses. More specifically, there is some work which is focusing on darknet data, not only telescopes. Basically, the work of Fashkayol in 2015 and 2016, where they analyzed the main activities of darknet, basically scanning worms propagation, or DNS query to identify DRDOs and other stuff. So all these works are for characterization. There are other works which are focusing on the visualization, how to visualize this darknet data to extract visually some useful information. There is a work of Van Riel et al. In 2006, where they provided INEDVIS as a solution, visualization solution, using 3D scatter plot and to highlight some visual patterns. And there is also the work of Inouye et al., where they're using a 3D visualization tool. It's a kind of globe that represents the internet, and we can see the traffic from one point to another point regarding the collected traffic